And welcome to this tutorial on the atomic simulation environment and the atomic simulation recipes, which are Python frameworks for working with atomistic calculations, and it contains libraries and a framework for also producing automated workflows. So thanks to all of you for coming. And the program is very simple. So first I'll give a talk here of about 45 minutes. And then we have a short break. And then Ask Larsen will take over and provide a more technical tutorial on the ASR, the ASE, and the ASR. I don't think he's planning a hands-on tutorial because that's complicated, but he will walk you through and give a demonstration of how this works in practice, how you can use it in practice. So this workflow environment that we have developed and that we call the Atomic Simulation Recipes is part of the NOMAD Novel Materials Discovery Laboratory, which is a center of excellence, a European center of excellence. And there, as you might know, there are a number of tutorials under the NOMAD Center of Excellence where we demonstrate the different software that we develop in the center. You can find the list on the NOMAD website, the list of tutorials. So please, if you have any questions, I think the easiest is if you just interrupt me during the talk and ask your question, because I'm not good at keeping track of the chat. And I think it's better we take the questions as we go along rather than waiting until the end of the talk. Okay, so since this is all virtual, you might not have a very good idea of where I am located. And I'm located in Copenhagen at the Technical University of Denmark, which is this little country here, north of Germany. And if we zoom in a little bit here on Denmark, then the capital Copenhagen is over here, close to Sweden. And a bit north of Copenhagen, 10 kilometers of Copenhagen, that's where the Technical University is located. And right now I'm sitting at home, but usually I'm sitting in a building over here. Okay. Now, let me start by say a little bit about the atomic simulation environment before moving to the actual topic of this tutorial here, which is the atomic simulation recipes. But it builds on the ASE. So I want to introduce that first. So I think historically the ASE was really the first Python library for atomistic simulations. It's almost 20 years old by now. And as you know, there are many of these Python tools, libraries, frameworks developed over the years that makes it easier to work with atomistic simulations. But the ASE was really the first one. And the main idea of the ASE was, and still is, to look at the DFT codes as some external black boxes, you could say, that can calculate energies and forces. Now the ASE has been developed further. So it's not just about energies and forces, it's also about the electronic structure, eigenvalues and wave functions and densities and things like that. But I mean, to make the point, let's just focus on energies and forces. And that was also where it began. And then the idea is to use Python to implement functionalities that do not depend on the actual DFT code. And that has the advantage that you can develop such functionalities even if you don't know the inner workings of the DFT code, right? You just know that you can give the DFT code an atomic structure and the DFT code will return energies and forces. And that also means that the functionalities you develop, for example, for structure relaxations or dynamics, they can be used with a lot of different DFT codes if you set up things in this way. So the ASE is an open source code. You can find it on GitLab, and it's actually quite a large community effort these days, and there's been 250 or more than 250 contributors to ASE over the years. So if we zoom a little bit in on the ASE, this is its basic structure. As you might know, Python works with classes. These are the main objects in Python. And the main class, these are different classes, and the main class is the atoms class. And the atoms can have a calculator attached to it. And that calculator, of a large number of different DFT codes or classical potential codes. So there, I'll come back to it, but there are many different codes here that have interfaces to the ASE. So you hook that onto the atoms object, and then you can also attach different types of dynamics. That could just be energy minimization or molecular dynamics, non-stochastic bands if you want to compute barriers. And then there are different analysis tools, tools for visualization, and you can add constraints and a lot more. But this is again just to illustrate the main points. And just to give you a more specific illustration of how the ASE works, or how you would work with ASE, here is a little example of a simple molecular dynamics simulation. So you start by importing whatever you need here. You can see there are a number of imports from the ASE. And in this case, we set up some atoms here that are just an FCC bulk crystal, or a 3x3x3 cube of an FCC copper bulk crystal. We do not use periodic boundary conditions. And we add some vacuum, 5 angstroms of vacuum around all sides of this cluster. And then we give the first atom a momentum in the y direction. And then we add a calculator to the atoms object. And in this case, it's an EMT calculator. EMT stands for effective medium theory. So that's an interatomic potential code. And we define a dynamics object, which is a velocity Verlet object that takes the atoms as input, and then a time step. And then we define a trajectory to which the output is written, and then we run the dynamics, or we attach the trajectory to the dynamics object, and then we run the dynamics for 1,000 time steps. So that's just to give you a flavor of what the ASE looks like and how to work with it. And there's a lot of tutorials on the ASE website that you can go and try out if you like. So a little historical notes on the ASE. So as mentioned, it started back in 2002. And here is the evolution of the ASE, the first version of ASE in terms of number of lines of codes. So you can see there's a substantial amount of documentation that was written back then. But then at some point, I can't remember when, there was a second version, and this version was abandoned. And then in 2008, a third version of ASE was started, essentially from scratch, as you can see, and that is actually the current version of ASE. This is still version 3 point something. And one thing you can see here is that the amount of tests is increasing a lot here compared to the original development. So this is one thing that we've learned along the way, that tests is really not only for COVID, but also for software development is really important. So there is lots of tests that are run automatically every night for the ASE, and checking that every time there is a new commit to the code, that the original stuff is still working as it should. Okay, it's a very active user and developer community, as you can see here. These are the number of issues on GitLab that have been created recently and closed, and some are still open. And the number of merge requests for ASE on GitLab is approaching 2,000. And here is an overview of the different codes, DFT codes and classical intratomic potential codes that are interfaced with ASE as of today. And you can probably find your favorite DFT code here somewhere among all these. I think there are about 40, something like that. Okay, so enough about the ASE. Now I'm going to switch to ASR. And ASR, Atomic Simulation Recipes, is an ASE-like framework. So it's similar to ASE. It's inspired by ASE in many ways. It's also using the ASE quite a lot for managing atomistic calculations and the data that they produce. So the difference to ASE is actually here, right? ASR focuses on the calculations themselves and the data that they produce, whereas ASE is a tool for working with the atoms, setting up the individual calculations, you can say, and looking at the output from the individual calculations. So ASR is now taking sort of this one level up and working with the calculations. And it makes it possible to create workflows that are required for high throughput computations. And these workflows, they work to a large extent automatically. A lot of the functionality in the workflows have been automated. ASR distinguishes itself from other available workflow codes by being simple, very transparent, so it's easy to see and follow what is going on. Relatively easy, I should say. Nothing with high throughput and automated workflow is really easy. And then it's also very flexible. So you can take this and you can tailor it for your own application, for your own needs. So it's not a big black box that you download and then you have to learn how to work with the system. It's the user that is in charge, and it's not the system that is in charge in this case. It's open source. You can find it on GitLab. And the hope is, or the goal is, that within the 3 years of the NOMAD COE, we are supporting a large part of the simulation codes that already have an ASE interface. We are not there yet. So currently the ASR works with the GPAW DFT code that I'll also come back to. But this will eventually be loosened up so that it can use other DFT codes as well. Okay, here's an overview of the main components of the ASR and how they are interlinked. You can see up here, this is the core of ASR. That consists of a caching system that is a system for storing the results of the simulations and maintaining the provenance, the metadata related to the calculations. So in practice, this is an invisible directory that is made in the folder where you run your calculation. So you don't have to really work with the output files from the DFT code or anything like that. That is all automatically taken care of by the ASR. But you can go to that directory and look into it if you like. So in that sense, it's very transparent and easy to follow what's going on behind the curtains. So the caching system is one part of the ASR core. The other part is the recipe. And the recipe is, to a large extent, a concept rather than something, concrete. But we have implemented made specific implementations of this recipe concept, and I'll come back to that on the next slides. Then there are the interfaces, the user interfaces down here. There's a command line interface. You can work with it directly in Python, which makes it very flexible. You can also work with it through a task scheduler, a front end to a task scheduler. And I'll say a little bit about one of the task schedulers that we are using, that we have developed, that we call MyQueue. And this task scheduler can actually interact with the HPC scheduler, Slurm, PBS, whatever, which are not always very easy to work with. So this front end makes that part easier. Okay. And then finally, there is an app interface here, a web app, that makes it possible to take databases that you have created from the results, that you have run, the data files that you have, the results file that you've created, you can make databases and you can present them as web pages. And then up here we have the simulation codes, and ASR interfaces or interacts with the simulation codes through ASE. So it uses functionality in ASE, and in particular, the recipes also use ASE to talk to the DFT codes. And then it also uses a number of other Python-based libraries. So I'm going to say something about the ASR core. So the recipe concept and the caching system, that is the core. The recipe, that is a Python script that performs a well-defined simulation task in a robust way and accurately, while it keeps track of all the metadata related to the calculations. That's what we call data provenance. And that is done automatically via the caching mechanism. So you don't, as a user, you don't have to worry about that. That is done automatically for you. And these recipes, they are independent objects in the sense that they take care of their own data provenance logging. And that means that you can work with them as individual objects. You can combine them through Python scripting or through the command line interface. But if you use Python scripting, it means that you can put them together as building blocks, and that makes for a very modular framework for setting up workflows. And these workflows can be as advanced as you like, because this is all done in Python. So you have all the flexibility of Python when you create workflows. So before saying what a recipe really is, I need to introduce the concept of an instruction, because a recipe, and that could, to become a little bit more concrete, that could be calculate a band structure. That could be a recipe that does that. A calculation of a band structure might include subtasks. Often there is sort of a main computational part where the DFT code is called, and it performs the computationally expensive calculation of the band structure. And then there might also be a part that is more like a post-processing part. And it's often useful to take your recipe and then divide it into separate tasks. And that's what we call instructions. So a recipe consists of a number of instructions. Sometimes it's just one, but it could be several. And this is also useful because other recipes might use instructions in other recipes, right? So recipes can use instructions from other recipes. And it also means when you're going to submit this to the supercomputer, different subtasks might need different resources, number of cores, amount of memory. So by breaking the recipe into instructions, you can make a more efficient workflow. So an instruction is a Python code. So the orange part here is really where your Python function sits. That's where all the action happens. And you need to feed some input arguments to your function, obviously. Then the blue part here is what we call the caching layer. And what the caching layer does, it sort of intersects and looks at the input arguments before they're evaluated. And then it looks in the cache and checks whether that exact instruction call has already been performed before. So the output of an instruction is called a record. I'll come back to that, but that is basically the output. That contains the result of the calculation and all the metadata that makes it possible to, for example, reproduce the calculation at a later point, if that's what you want to do. So first, the caching layer looks in the cache. Has that exact instruction call already been performed? If yes, then it just reads that record from the cache and returns it. And it's in that sense circumvents the costly evaluation of the function here if it has already been done before. If it hasn't been done, if it's not in the cache, then it evaluates the function, creates the record, meaning it has the result of the actual function, and then all the relevant metadata. And then it puts it in the cache and returns it. So that's an instruction. So now we come to a recipe. So a recipe now, as I said already, it consists of a number of instructions. And in this case, we have 3 instructions. And the blue frame around the Python function, that is this caching layer. And you don't have to worry about the caching layer. If you want to write your own recipe, you just write a couple of lines of codes, and then the caching layer is automatically activated. That's the only thing you need to do. And that caching layer is what talks to the cache, as you can see by these dashed lines here. It can save to the cache, and it can read from the cache. There is always a main instruction of a recipe, and that's the instruction that the user of the recipe interacts with. So that takes the input arguments here, in this case A and B, and then it evaluates the function. And you can see this instruction here calls instructions from the recipe itself, the calculate and calculate correction instructions here. But it can also call instructions from other recipes. And this is what we call dependencies. So a given instruction can depend on other instructions. And this dependency list here is part of what is saved in the record. So here you can see what the record contains. It contains typically an atomic structure, the atomic structure that was the input for this recipe. Then obviously it holds the result of the calculation. It holds the version of this instruction. This is something I'll come back to later on when talking about data maintenance. It holds the input arguments for the instruction. It has a unique ID, and then all the dependencies, migrations, and the resources that were used for executing this recipe here. So that's the main structure and content of a recipe. Okay, so maybe I should ask if there are any questions out there at this point. I can see that Mariano has a question, perhaps. He has a raised hand at least.
Yes, hello. I'm sorry, I raised my hand, or this little hand a while ago, and then I forgot about it.
Okay.
No,
okay.
my question, okay. But no worries. I can remember my question anyway. So the question was about the collaboration framework. I mean, I have seen that you are open for collaborations in the development, but I was wondering if there is any requirement to collaborate. Do I have to register anyway or somewhere, or do I just clone the repository?
Okay, I think
trying to see some possible collaboration.
Yeah, I think this is a good question that you should probably ask later when you have the more technical tutorial, because ask Larsen, who is going to take you through that tutorial. He knows all about that.
Okay. Cool.
All right.
Good,
other questions? Yeah. Michael Wallach has.
Yes. Can you hear me?
Yes.
Okay. So this is more a general question, and maybe it's coming later, but just giving this overview of the destruction of ASR, it seems to me at least quite similar to the concepts that have been laid up, and especially the caching and the interface to different codes. I mean, using different stuff, of course, but I wanted just to ask, and also the interface to yes, this slide exactly, to task schedulers and to a database, and this modular framework. And I have been using AIDA for some time, but now switched to Fireworks, so I'm not familiar with the new developments of AIDA, and of course I'm not familiar at all with ASR, so there can be a huge difference that I'm just not seeing right now. And I just wanted to ask if you can comment a little bit on that and what you think are the unique advantages compared for example, to AIDA for this ASR?
Right. That's a very good question. I should say I'm not at all an expert in AIDA. I've actually never really used AIDA. Maybe I'm not the right one to answer it. But what we have tried with ASR is to make something that is simple and transparent, so that the user is really in control of everything. It's easy to get started. At least that's our intention, and we hope that this will also be the case. That's what we've heard so far, that it is, compared to other workflow codes, easy to get started. There's not a very large sort of training period before you find out how things work. So it's in that sense, it is simple, but it's also efficient. So we give the user sort of the building blocks, the main functionalities. And for example, this caching mechanism here that is really solving the difficult problem of keeping track of all the metadata and keeping track of whether calculations have already been performed or not, and automatically just reading the result if it has already been performed. That is sort of something that is not easy to implement and keep track of yourself as a user, and that is provided by ASR. Then the recipes here, that's a very open thing. That's why I said it's more like a concept. So you can write your own recipes if you like. So in that sense, if you know ASE, it is similar. You can use the functionalities in ASE as a library, but you can also write your own Python code, because often it happens that you want to create a workflow for something, and maybe the functionality that you need is not exactly there, but then you can develop it fairly easily with the ASR, and of course use the functionality that is already there that you need. So I would say it's simple, it's very flexible, and because everything is Python code, it's extremely flexible. And then it's working via the ASE. So eventually, when we get this all working, you can work with a lot of different DFT codes with the ASR here.
Okay, thank you, Lars. Maybe I will ask more specific questions later, but I'm very interested.
Sure. Yeah.
And I think like all these points, especially the caching, I'm completely with you. That's a very important part that is not present in a lot of other options. It is in AIDA, but maybe differently executed. Thank you.
And another thing that I can mention at this point is that this is very local, right? So the cache is just running locally on your own machine. And if you want to collect a database, for example, once you've done with your project, you just collect the database over here, and then you can show it as a web page. So it doesn't run on some central server somewhere. It's all very local, which is another I think difference from some of the other workflow codes. Okay, are there other questions at this point? Otherwise, I'll just continue. So that was the recipe. Here you can see what we call the recipe library that we have at this point. We have about 40 of them, and of course, all the time we get more and more. And most of them are GPAW specific. GPAW is our DFT code, the DFT code that we develop as well. But you can either you can wait until we have really made all the recipes DFT calculator independent, because that is the goal that we have. We want to do this such that you can run the same ASR recipe with different DFT codes. This is obviously very challenging, and it will require quite some work, and we are not there yet, but that's the long-term goal. If you cannot wait for that, you can either use the GPAW code, which is a nice code. I can strongly recommend it. But you can also take these recipes and just use them as templates, and then change them such that they work with your favorite DFT code. In particular, if this DFT code has an ASE interface, that might not be so difficult. So you would write your own recipes, starting from one of the existing recipes and then just changing something here and there. That might be simple for some recipes and more challenging for others, but that is certainly a possibility. So the GPAW code, I've mentioned that a couple of times, and it's a PAW code. It's in many ways similar to the BASP code. It's open source, however, you can download it for free. It has a GPL license. It has, and that's quite a unique feature of the GPAW code. It has 3 different types of basis sets. You can work with a real space grid, which is very efficient if you want to parallelize over, if you have large systems, because you can parallelize efficiently over real space domains. It also has plane waves that are very efficient for smaller periodic calculations. And then it has numerical atomic orbitals, so we call LCAO, linear combination of atomic orbitals, similar to the siesta code, if you know that. But this is PAW rather than pseudopotentials. And it has time-dependent DFT and many-body perturbation theory, phonons, electron-phonon coupling, Landauer-Büttiger electron transport, and then it's very well connected to the ASE and the ASR, as mentioned. Okay, so let me demonstrate just very briefly the command line interface and what you can do with that. So this is very convenient if you just want to run a single recipe, or if you want to look into the cache, look at the results that are in the cache. So for example, you can write this line here, ASR cache ls name equal ASR.gs. GS is the recipe for a ground state calculation. So that's just a one-shot DFT calculation. If you write this, then you get all the records in the cache that have been produced by the ground state recipe. If you want to run the ground state recipe, you just write run ASR.gs. So here's another example. If you write this on the command line, ASR will calculate the band structure. It will run the band structure recipe for the structure that is called structure.json. And once that is done, you can take a look at it by writing ASR results, ASR.bandStructure. And then you would get this figure here where you see the band structure. The colors refer to the projection of the spins in the Z direction. And this is the Brillouin zone with the band path and the position of the valence band maximum and conduction band minimum. So you don't have to do anything to get this kinds of plots out. You just run the recipe. So one thing that I probably forgot to mention when speaking about the recipes is that the recipe, of course, should be able to perform the calculation, in this case, the band structure. But it should also have a part that how to present the results. And in this case, there is a figure here of the band structure, and there is the Brillouin zone. This is also something that is coded into the recipe. And then there is also the part about how to present this as a web panel, which I'll come back to later on. But there are these different parts to a recipe. Okay, that was the CLI. You can also work with this in the directly through Python. And you can also work with the ASR using a front-end task scheduler. And let me say a little bit more about that, because we have developed what we call MyQueue. I guess this is similar to Fireworks. There's a tutorial on Fireworks tomorrow, which I definitely recommend that you attend. And I think that MyQueue is a simple a simple version of Fireworks. What MyQueue can do is it can give you your own, you can call it a personalized queue in your on the supercomputer. It's decentralized. It just works on your own system. It's simple. Yes. Is that a question? I think it was just some background noise. Okay, it supports these schedulers here, LSF, PBS, and Slurm at the moment. You can very easily get an overview of all the jobs you have in your personalized queue. So you can see which jobs are done, which are still queued, which have failed, and so on. And I'm sure Ask is going to demonstrate this in the technical tutorial afterwards. It makes it possible to submit thousands of jobs in one command, via the command line interface that MyQueue also has. And then there is also a Python interface that you can use also to connect to the ASR. And that makes it possible to make advanced workflows. The way that works is you define a so-called dependency tree of tasks, and those tasks could be recipes from ASR. Okay, so a task is just a job that you can submit to the supercomputer. And then the dependency tree that MyQueue can use takes this simple form: if X is done, submit Y. Okay, and these X and Y, they could be recipes, but in principle, they could be anything. So MyQueue can be used with ASR, but it is actually independent of ASR. You can use it for submitting any kinds of jobs that you like. Okay, so now we come to the database part. So ASR has a number of tools for working with ASE databases and presenting them as websites. So ASE databases are really simple to work with. You can install it very easily using this PyPy command, and you can port the ASE database to many different formats. So there are backends here: SQLite, Postgres, MariaDB, MySQL, and I think there are even more. So once you have an ASE database, you can port it to any of these formats here. You can, with ASR, with a simple command, you can take all the results you have in a given folder tree. When you run ASR, it works at the file level. So it has these caching directories where it puts all the records that results after running recipes. And now you can collect all these records into a database. So this will now be an ASE database consisting of records that have been produced by ASR. You can also go the other way around. So if you have a database, you can unfold it into a folder tree. This can be useful if, for example, at some point you've created a database, and then a couple of years after you find out that you want to continue on that project, but maybe you've lost the files in the meantime, or you want to move them somewhere else, and then you can just take your database and unfold it back to a folder tree. And then once you have a database, you can create easily web pages. And I say easily because the recipes, they actually have a part in them that tells how it should be formatted, how the results should be shown on a web page. So again, as a user, you don't have to do much if you have an ASE database consisting of records. You don't have to do much to turn that into your own online database. You can also add explanatory descriptions to all the data on the web page, and it's possible to create links between different rows of the same database or between different ASE databases. I'll show you some examples of that later on. Obviously, I realize what we also should put into this is a functionality for uploading to the NOMAD database. But this is not currently in place. Okay, so now let me give you an example of a project that we've done using the ASR. So this is the computational 2D materials database, the C2DB, which is a database for 2D materials. I guess most of you have heard about 2D materials, but graphene, I'm sure you've heard about that, but there are lots of other atomically thin inorganic materials that are known as 2D materials. And we've performed this high throughput study of about 4,000 of such crystals. And we've not just calculated their structure, but we've calculated a range of different properties for these materials. So historically, the C2DB project started, I think, back in 2016. And at that point, we didn't have the ASR. So what we did at that time was we wrote Python scripts that could perform different types of calculations, relax a structure, calculate a band structure, calculate a Raman spectrum. But we didn't have this caching functionality in place. And that meant that all the people working on this, PhD students, postdocs involved in this project, they had to do a lot of manual, very tedious work in ensuring that we didn't overwrite old files and we didn't run calculations that we had already run. And, not to talk about the data provenance. If we had a result, could we reproduce it at any later time, right? So this was not at all in the beginning systematized. But I think going through this very painstaking process of creating the C2DB, or at least beginning creating the C2DB without the ASR, that was really what you could call a necessary evil, because this was really the way we learned how to build a workflow tool that really works. I mean, to do something like that, you need a real problem to solve. And in our case, that was this C2DB database. Unless, if you don't have such a practical problem to actually work on, then I think there is a big risk that you develop some kind of project that has a lot of nice features in theory, but then when it actually comes to working with it, it's maybe not that efficient. So right now, the entire C2DB can be run with a single ASR or MyQueue command. This is actually MyQueue. It runs a workflow, but what that workflow does is it submits recipes, ASR recipes. And this single command here will then launch a number of recipes, 23 to be exact, for more than 4,000 different materials. And this amounts to a total of, we've estimated, about 60,000 individual DFT calculations that are then run with this single command. And the success rate of the calculations is actually more than 99%. The few calculations that are not successful are typically because the Kohn-Sham convergence is problematic, and then we would need to go and fine-tune manually parameters in the scripts. But all these things about setting the parameters, that's also something that we really take care of when we write the recipes, right? So a good recipe should have parameters set, should work such that it is robust, that it doesn't fail, right? So that you can just run it for any type of system, whether it's an organic molecule or an inorganic solid, 2-dimensional, 3-dimensional, it should just work. And as you can see here, this is in fact the case. In the end, what we have here is the C2DB database. Everything you see here is something that has come out directly off the ASR. You can produce these kinds of web pages with the ASR. So now you can go and search for a material that could be MOS2. Then you get a list of all the materials that contains molybdenum and sulfur. And then you click the one that you want to take a look at. And then you can see here you get a summary page with sort of the most important basic information about that material. And then here you have panels that you can click. These are different properties that we have calculated. And you can see these question marks. So if you go and click a question mark, you get an explanatory description here of what this is. In this case, that's an effective mass tensor. So what is an effective mass tensor? And there is a reference to a paper here with some more background information about that particular property. If you click one of the panels, not the question mark, but the panel itself, you get the results. This was the band structure in this case of MOS2, and here is the Raman spectrum of that particular compound. Okay, so finally, data migration. this is really about updating, maintaining the data, and transforming the data. And this is really important. This is something we discovered quite late in the process. So that's the newest development of the ASR. But if you update at some point a recipe or an instruction, there could be many reasons for doing that. That could be fixing a bug that you've realized, or it could be just a general improvement of the recipe, or it might be that you want to reorganize the record that the recipe produces, right? You want to plot things, or sort of not plot, but store the data in a different way than it used to be. Then you also need to change the recipe. But if you do that, then it means that all the old records, all the old data that you have produced with that recipe is now inconsistent. And therefore, you need tools to bring that data up to date. And to do that in an efficient way, ASR has a versioning system. So a recipe or an instruction, in fact, has a version number. And that makes it possible to identify whether a given record is actually something that has been produced with an older version of this recipe. And if so, then you can migrate them, transform the records such that they become such that they correspond to the output of the newest version of the record. So whenever you migrate a record object, there is a revision history that documents the change that is being updated. So for a given record, you can go in and you can follow the revision history and see whether this record has actually been subject to migrations. So that is part of the data provenance. This is actually, you can say, more than just data provenance, because this is a dynamic data provenance that also makes sure that old data can be brought up to date with the newest version of the ASR. And that's important if you have an old project that you want to continue, that you can take that old data and bring that up to date so that you can continue the project with that data. And here's some graphics that just illustrates how we do that in practice. So you have your recipe library, all the recipes that you're working with. Those recipes have a migration object here, a migration selector. The selector here can go in for a given record and say, is this a record that could be migrated? And then it has a transformation that performs the migration. So you take all the migration selectors in your recipe library, then you take all the records in the cache, and then you check using the selector which of the migrations should actually be applied to that particular record, if any. And then you make what we call a migration strategy, and then you apply all those relevant migrations, and then you put the resulting record back to the cache. So in this case, there was a given instruction here, instruction Z, of version 1 that has been updated to version 3. That could be, of course, if there is a bug that has been corrected in the recipe, you need to run it again. There's no way around it. But sometimes you don't need to run the expensive instruction. It might be just the post-processing parts of the recipe or something else that you need to run, and then automatically this expensive DFT calculation step is not performed, and only the easier parts of the calculation are performed. And all this is done by the migration module. Okay, so in summary, I've gone through the ASR that consists of the ASR core that has the recipes and the caching mechanism that takes care of all the data provenance control. Then I've talked about the ASR recipe library that we have now, about 40 different recipes. And these work currently with the GPAW code, but we are going to make them work with other DFT codes as well in the future. I've talked about how you can create databases using ASR from a folder tree, or you can go the other way around. You can generate web pages automatically, relying on the implementations of that in the recipes. And this is very nice because it makes it easy to present your data to the outside world, or just internally if you have a project with many contributors. It's just a nice way of sharing the project, and you can look at the status of the project, and you can go and look at the data during the course of development of the project. MyQueue is a personal, lightweight, local task manager. It's a front end to the often very complex task schedulers that are installed on supercomputing systems. So it makes it easy to talk to the scheduler, and it's very useful for high throughput projects. So let me just end here by summarizing the main. What ASR really has as nice features here is it's very flexible. It's based on Python scripting, so that gives you a lot of freedom. It's very modular. You have these independent main components, and the recipe library also supports that modular design of workflows. It's local in the sense that you have your data locally, and you can access the data via the command line tools, so you don't have to go in and read any of the output files yourselves. There are simple tools that the user can use to access the data there. It communicates with simulation codes via the ASE. That makes it compatible with many different DFT codes. Eventually, at least, it will become. And then it's pragmatic in the sense that it's, as I said, it was developed during the development of the C2DB database. So in that sense, it focuses on simple solutions that work in practice. Okay, and very importantly, I should thank the people who actually developed the ASR. So Jens Jørgen Mortensen, he wasn't that much involved in the ASR, but he's the main developer of the GPAW code, and also very active on the ASE, and he also developed the MyQueue scheduler front end. Then Morten Gjerding was a PhD student and postdoc in the group for a number of years, and he's the main architect behind the ASR. Ask Larsen will be responsible for the technical tutorial that starts in a few minutes. He is working, has worked a lot on the ASE, and is also now taking over on the ASR from Morten Gjerding. Fabian Bertoldo, Torbjørn Skovhus, and Asbjørn Rasmussen have also contributed to the ASR. And funding is from the NOMAD Center of Excellence, the ERC, and the Danish National Research Foundation. So that was the end of this overview talk. And I think if you have questions, we can take them. What time is it? We can take questions. If you have burning questions, we can do that now. Let me see if there are any. Doesn't seem so. Then, okay. There was one from Joshua.
Hi, yes. I was curious for defining whether a material is magnetic or not. What is the threshold that you set?
Right, the criteria for determining whether a material is magnetic or not. I think the criterion we use there is whether, whether the maximum moment on a particular atom is larger than 0.1. If that is the case, then we treat this as a magnetic material. And if it's not, then we continue with, then we treat it as non-magnetic.
Got it. Thank you.
That is the default. But again, once you take down that recipe and you run it, you can go and change that yourself. And in that sense, you know, it's very flexible. But this is what we have found, at least when we work with GPAW, to be a reasonable threshold. Are there other questions?
Yes, I have quick questions. Question about because it's about the robustness. You said so the recipe should be constructed in a way that default parameters or parameters are set in a way that it works for every structure or every system. I'm curious if, you know, this is just taking, you know, very, let's say, high energy cutoff or k-point grid or something just to be sure that it's converged, or if it's a little bit more, you know, logical, or if you have a lot of logic there to choose these parameters, and also then during execution, if there is some kind of error checking.
That's an excellent question. What we've done mainly is to choose the parameters a bit conservatively, as you say. So make sure that plane wave cutoff is high enough, and k-point grid is sufficiently fine. But we have also some checks, right? Where if this is metallic, then you can use a higher Fermi smearing and things like that. So there is some logic or some intelligence in there as of now. But again, this is something that will probably be improved in the future, and everybody is also very welcome to join the project and contribute with whatever insight and skills you have in developing these recipes, because as you say, it's actually a tricky thing, right, to make things robust. Error handling is another thing. If something doesn't run, then we should be able to catch the calculation and resubmit it again with more appropriate parameter settings, so that it hopefully will run. This is on the to-do list. I don't think it's going to be that hard to get something that will work. Most of the times you will never get to a point where it works 100%. But I think already with what we have now, without this error control, but with the current recipes, it is actually fairly robust. Another challenge is, of course, that this is going to be DFT code specific. So if we want to do something that works for a wide range of DFT codes, then that's going to be challenging, but I think we can manage.
Maybe a quick follow-up question to this. Thank you for the answer. Is so you say you have no error checking now, but it's very robust. I mean, you had this 99 point something accuracy, but let's say we have one calculation in, let's say, a larger workflow that fails. Is there an easy option to say update, let's say, the smearing or some other parameter which you think will aid convergence, and then, you know, rerun the workflow? And I guess with the caching, this means that all the calculations that worked up until this point will not be executed again, and it will just run through and give you the same results after you update this specific calculation. Is that true?
Exactly. That's exactly the idea. So if your workflow has stopped at some point because a calculation didn't run, and then everything following that couldn't run, then you of course you have to figure out, since there is not an automatic error correction at this point, you have to manually. Then when you go and you look at your queue with MyQueue, you will see that particular job has failed. Then you can go in and change that parameter and then resubmit the entire workflow again. And then all the steps that have already been executed before successfully are then skipped because they have already been done, and then the workflow will just continue where it stopped. So in principle, it's just the big workflow. You go to the root of your tree, your folder tree, where you run your calculation, and you resubmit your workflow script again from that point. Then it goes down in the tree and submits it everywhere, and it just continues wherever it needs to continue. Was that clear enough?
Yeah, that was perfectly clear. Thank you.
Hi, can I ask something?
Sure.
Hi, thank you for the nice talk. Could you say a bit more about which code parts are GPAW specific that one would have to change in order to run with some other code?
Yes, well, there are lots of recipes. most of them are GPAW specific, I should say. So here is the list. And you can see there are things that work on the atomic structure that is not GPAW specific, but everywhere where you see there is a DFT calculation involved, that is using GPAW as of now. But sometimes, for example, a relaxation, there it will be fairly easy. Maybe it has already been done. I know that some of them are already working with VASP. But in other cases, it's much more tricky to change it. So I think that's the best answer I can give at this point.
Okay, thank you.
Okay, any more questions?
Yes, I would like to know this caching. When would you start a new cache? Every day, or would the whole group use the same cache so that nobody recalculates something?
The cache is there is a cache per directory.
Okay.
So that means if you and your colleagues are collaborating on a high throughput project, you could say that all users have read and write rights to all the folders there, and work in the same folder tree, right? Then typically each material you would have a folder for each specific material, and then within that folder there is a cache.
Okay.
But that is actually not, that's how we typically do it in practice. But in principle, you could also just work with one cache. That could be, so what ASR does, it goes up in the folder tree until it meets a cache. And then it stores the results in that cache. So you could have a cache in the root of your folder tree. And then all the results, everything that would be cached would go into that cache. So to create a cache, you just, I think you run asr.init cache, and then it creates the cache there. So that is, again, something you can control yourself where you want to have the cache. Okay?
Yep.
More questions? All right, then I think we should end here. I'm sorry for going a bit over time, but I think your questions is really the main thing. That's the main reason why we're doing this. So let's take a maybe a 15 minutes break as was originally planned. So then we reconvene here at 20 minutes past 11, and then Ask will give you a demonstration of how this actually works in practice. Okay, so see you at 20 past 11.
Okay, I can see that recording has started. So